All right, let's get started. So I'll be talking about SIMIT. SIMIT is a language for computing on sparse systems, right? What a sparse system is in this case is like something like a mesh, right? Because SIMIT is used for simulating graphical simulations. So that could be a video game, a movie, mostly a video game, but for computing um, graphics, right? But a sparse system is unique because it's a system that's comprised of mostly zeros, mostly nothing. Um, a case of this would be um, well, most space in a video game is just empty space, right? You don't have to compute anything. There's nothing going on in every single unit of space in a video game, right? SIMIT is also built with it's built with convenience and performance in mind, right? So I'll be comparing SIMIT to other conventions for doing simulations, such as this regular C++ and all the libraries that go with that for things like linear algebra and matrix math and all that other stuff. But SIMIT is a language that is built for just the purpose of simulations, right? So there's all these extra benefits baked into the language itself that we can take advantage of. So compared to MATLAB, which is another popular solution for simulations, it has about as many lines of code as MATLAB, because MATLAB is a more high-level solution, but it's about as performant as regular manual C++, right? So it's a good um, combination of the positives of both of these solutions. A typical problem with computing sparse systems is they consist of multiple objects that don't interact very well. So you can think of these, some of these objects would be the meshes, so the physical message that you see, physical simulations, structured grids, fluid simulations, behaviors, all of these things have to work together and it can incur some serious performance costs. Here's an example of where um, it's a graph with MATLAB and regular hand optimized C++, right? So C++ requires a lot of coding, a lot of source lines, but is very fast. You can get a lot of frames out of it. As you can see, MATLAB, which requires very little source lines, very little code, is very slow compared to regular C++. So you have the typical example of high abstraction, which is slow, and then low abstraction, which is very fast, right? So the idea of SIMIT is it's going to be on the very bottom left of this graph. It's going to have very little source lines, be very fast. So let's talk about mesh simulations, because that's what you mostly work with here. So a mesh simulation is something like this dragon to the left here, right? This is a mesh of a dragon, and the dragon is floppy because you applied a sort of like floppy behavior, physical behavior to this dragon, right? So we have things like structures, which is this dragon is a structure, right? Which is done with meshes, right? And then we apply behavior like motion and fluid to that mesh. We do that with linear algebra because we need to map over all of the pixels in that mesh. But the merging of the two is very costly, right? There's a wall between the two, and you have to do it very very intelligently. And this is typically done with some sort of loop that loops over the sparse structure, in this case the mesh, and inserts values into a sparse matrix, right? This is what so you turn the mesh into a sparse matrix, and then you loop over it, and then you apply linear algebra to it. And you do this in C++ typically, or MATLAB, and you use some sort of libraries to do this. But this loop is very prone to off by one errors, right? Because you're doing it over in a matrix. It's all like arrays, and you can easily get off by one errors. And this is slow if not optimized or parallelized. But the SIMIT programming model lets you express both the structure and behavior in the same simulation loop because SIMIT is built for this kind of simulation. So in the SIMIT model, behavior, which is fluid motion or the floppy motion of the dragon, is expressed as just linear algebra like you expect, but structure is represented as a hypergraph instead of a mesh. So a hypergraph is something that where each edge can have infinite endpoints. And then a key to SIMIT, once you have these two things, is a vector matrix assembly. which lets you go from a hypergraph to it lets you go directly from the structure in this case, which is a hypergraph, to a matrix directly, automatically, and then you automatically apply the linear algebra to it in the same loop. So this is all built in, and it's tightly cohesive. And so this allows you to compute your behavior with linear algebra very easily. Another benefit of CIMIT is it compiles the CPUs and GPUs just the same as it would either two. You don't need to change your program. Generally, if you're writing for a GPU, you need to write different code. You write a lot more code. CIMIT is not the case. Of course, compiling the GPU will give you around a 2 to 20 times performance. This puts you into the interactive realm, which is like a video game, right? This can work for video games. And unlike other simulation methods, you can stay at the same lines of code and don't have to change when you go from a CPU to a GPU. Here's an example of what I talked about on slide 7, which is a CIMIT model. You have a hypergraph, in this case the dragon. This represents the look of it. That automatically maps to a vector-sized matrix assembly, which you can apply linear algebra to, right? And this then updates the hypergraph. This is a very tight loop. It's very quick, fast, and it doesn't require you having to switch between these two separate things, which is working with the structure and the behavior. It's all integrated in one loop. So another 3 benefits would be, one of them would be, of course, the conciseness. So like I said, this has MATLAB-like syntax. It is very abstracted. This lets you do algorithms in a compact and then readable form, right? The CIMIT matrices are assembled, from hypergraphs and are indexed by hypergraph elements, which simplifies the indexing code and eliminates bugs, right? That's the whole point, is to make all of this index math, which is, of course, we all know error prone, right? When you always have these index out of bounds methods, right? Index out of bounds exceptions. CIMIT's point is to just avoid those by putting in these language features. CIMIT is, of course, expressive. It consists of linear algebra operations that is built in and are augmented with control flow. And then the powerful hypergraph abstraction that I showed before allows easy specification of complex data structures, like the dragon, for example. It's pretty easy to express. And then CIMIT, lastly, is fast. So the CIMIT compiler produces high-performance code for you that's similar to C++. It's comparable to hand-optimized C++. It's probably a little bit slower, but it's pretty much there. And simulations can be written as easily as a traditional prototype because it is, like MATLAB, so it's fast in terms of like runtime, and it's fast in terms of productivity, how much time it takes to write. And then, of course, it's as fast as high-performance implementation of the C++ code. All right.